Hi everyone, so in the previous section we discussed what will happen to the charge stored to the voltage cross capacitor or to the capacitance, the equivalent capacitance, or to the energy stored to a capacitor when you have multiple capacitors connected in series or parallel. Okay, so right now we are going to move on to the next section, which is section 3, which we are actually going to reverse a little bit and focus on the process of charging and discharging a capacitor. So chapter 2 section 3 is on charging and discharging of a capacitor. Oops, sorry. Okay, so in this particular video, we are going to focus on the first part, which is the charging process. So we are going to observe in detail how does the charging process happens to a capacitor, and we will study whether the charge stored increase or decrease, the voltage whether it increase or decrease, or the what do you call it, the current whether it's increase or decrease. So these are the things that we are going to study during the charging process. So right now over here we have a charging circuit. Okay, so this is a charging circuit. Okay, as you can see over here, a charging circuit consists of a capacitor, and to charge it, you need to connect it to some sort of a power supply. The most simple one, it's a battery or a DC power supply. And over here, you have a resistor. Okay, the resistor is to control how fast the capacitor being charged. Okay, so this is a very basic charging circuit. But what I want you to think about is which component here plays the role as the energy supplier, and which components plays the role as the energy consumer. Okay, so if we know the power supply here, as the name itself implies, it is the component that used to supply energy to the circuit over here. So in this case, our battery will take the role as an energy supplier, and the capacitor here is to store energy, right? The function of capacitor is to store energy. So that means, like, where does the energy come from? The energy comes from the battery. So the battery will distribute the energy to the capacitor, and when the capacitor receives the energy, it will store the energy. So that sort of makes sense, I think. Okay, how about the resistor over here? We know that resistor are just components which regulates your current, or is mainly used to regulate your current. So what happens is, if you have energy being directed to a resistor, what happens is it will be dissipated as heat. Okay, so your resistor technically get hotter because it's going to dissipate the heat, the energy that is being received by the resistor over here. Okay, so by that discussion over here, we know that the battery will be the energy supplier, and the capacitor and the resistor, these two components itself, will be the energy consumer or the energy receiver. So from that statement itself, we can sort of come to a simple logical statement that the supplier is the battery, the receiver is the capacitor and the resistor. So by the idea of conservation of energy, assuming that this is an ideal circuit, we can probably say that the energy supplied by battery will have to be equals to the energy received, right? Okay, someone supplies, someone will be receiving the energy. Who will be receiving the energy? It will be received by the resistor together with the capacitor. Okay, so when resistor receives the energy, it will dissipate it as heat, which just release it to the surrounding. If a capacitor receive heat, if a capacitor receive energy, it will store it in the form of electrical potential energy. Okay, so based on the idea, we know that any kind of energy, if you receive energy or you supply energy, it will cause the charge to experience a change in energy. What does it mean? Okay, let's say if you have a charge and this charge here is being pumped by the battery going from the negative terminal to the positive terminal, right? As it passes through the battery, you go from a low potential region to a high potential region. And this potential difference that it passed through here, if you think about the idea where delta U is equals to Q delta V, right? Okay, this is chapter 1. So this here is a delta V, is a potential difference. And right now you have a charge Q which is going to pass through it. So when you pass through it, this charge here will experience a delta U. So in this case, this is a positive delta U, or it's an energy being received from the battery. The battery provide the energy to this Q over here. That's why the Q here is being supplied with energy. Okay, so once the charge is being supplied with energy, what happens is the charge has already reached a higher potential region, so full of energy will be coming out from the circuit over here. Then the energy that it holds right now will have to be distributed either to the capacitor or the resistor, or both of them in a certain combination. Sometimes it will be capacitor receiving more, sometimes it will be the resistor receiving more. Okay, but the idea is it's a charge that pass through the battery that receive the energy from a battery. So the charge holding the energy when it come out from the battery will go down the circuit and distribute the energy either to the capacitor or the resistor. Okay, depending on certain combination as the charging process goes by. Okay, so you have to think, if you think about it in the logical, sensible way, once it has fully distributed the energy that you receive from the battery to the capacitor and the resistor, it should come back to the negative terminal with 0 energy left. Okay, let's say this is a 1 volt battery. If this is a 1 volt battery, that means the potential difference over here is 1 volt. So if you have 1 coulomb of charge passing through the battery, you will gain 1 joule energy. Okay, so the 1 joule energy, maybe 0.8 joule is being passed to the capacitor, 0.2 joule is passed to the resistor, so you come back here with 0 energy left. So the energy supplied by the battery is 1 joule, and the energy received by the resistor and capacitor should add up to 1 joule. It can be 0.8 received by capacitor, 0.2 received by resistor, but you add them up, they should be coming back to the same 1 joule which is supplied by the battery. Because, or else, where does the energy go, right? We learn about conservation of energy, so it has to be transformed into somewhere. Okay, so by that idea, we know that it's the same charge that is going to pass through the battery, the resistor, and the capacitor, right? So we can ignore the Q and focus on looking at the potential difference instead, because the Q is a constant over here. It's going to pass through every single component. So let's just ignore the Q and talk about the voltage or the potential difference. So we can say that the potential difference of the battery is how much? Then it has to be equal to the potential difference of the capacitor together with the potential difference of the resistor. Okay, think about it in terms of energy. It's just the same thing actually. So Vs here represents voltage of a power supply, and it should be equals to the energy received by the resistor. That's why I'm going to call it Vr, and the energy received by the capacitor, I'm going to call it Vc. Okay, if you just multiply Q to every term, it will become the change in energy, the gain of energy, the loss of energy. Okay, so let's just ignore the charge for now because it's the same thing all over different components. So let's focus on looking at the voltage only. Okay, so this is the voltage of the power supply. Okay, let me probably, this is referring to power supply. This is referring to the resistor, whereas this is referring to the capacitor. Okay, so we know that for power supply, what you're going to use is probably a battery or some kind of DC power supply that you use in an experiment. So for those kind of battery, right, they come with a certain voltage already. Okay, today let's say you buy a battery, let's say a simple, I'm not going to, this is not an advertisement. Let's say you're buying just an AA battery. A AA battery over here, if you can find, I don't know whether they label it or not. Okay, over here they write this is 1.5 volt. So that means by this battery here is 1.5 volt. As long as you're using it, it's 1.5 volt. You cannot change it to become 3 volt. You cannot change it to become 5 volt during the charging process. It's a constant 1.5 volt. So every battery has its own voltage and it's a fixed value. That's what I'm trying to convey over here. So because it's just a fixed value, I won't be expressing it in other things. It's just voltage of the power supply. Okay, VR over here is the voltage across the resistor. Voltage across the resistor, we learned about resistor in chapter 3, which is later. It will be expressed in terms of Ohm's law, right? So I'm going to write it as V is equals to IR. Okay, so this VR here is re-expressed as IR, whereas this VC over here, voltage across capacitor, we know about C is equals to Q over V, right? So rearranging it, you get V is equals to Q over C. Okay, so this is the equation that you have if you expand each of the voltage over here. Okay, so if you are talking about a charging process, what we will expect is that a charging process, the charge will become more and more, right? You store more and more charges in your capacitor. So by that logic, you should expect that your Q to be increasing. Okay, at the same time, for your capacitance refer to a single capacitor, the value of a capacitance of a capacitor. As I mentioned a few times before in previous video, especially in section 1, if you're using a capacitor, the capacitance won't change unless you do something inside the capacitor. Let's say you change the area of capacitor, you change the distance between the capacitor plates, or you insert some kind of dielectric inside the capacitor. So if you're doing nothing to the capacitor, you're just changing a power supply, you're just charging it, you're doing nothing inside the capacitor, the capacitance value shouldn't change. So therefore, this C over here should be a constant. Okay, so by this logic, you know that if Q is increasing, C is constant, this voltage of the capacitor here should technically be increasing. And that's why this should be increasing. Okay, but we already mentioned just now that this voltage of the power supply is actually a constant value. Okay, this voltage of power supply is a constant value. So if this voltage of a power supply is a constant value, that means by the left hand side is constant. So if the right hand side have one term which is increasing, the other term will have to be decreasing, so that the sum of it will still become a constant value. If this voltage of the capacitor increased by 5 volt, this voltage of the resistor should decrease by 5 volts, so that the sum of it still remain the same. So you know that this VR over here will most probably be decreasing. Okay, but decreasing over here means by IR over here, something have to decrease. But if you look at a resistor come with those resistance stripes, right? You learned before in the resistance table, there's red, yellow, brown, gold, there's stripes. So from the stripes, you're able to read the resistance value based on the resistance table, right? But the problem is, try to think about it. If you are charging a capacitor, does your resistor stripes, those color bands, does it change color during the charging process? Does it initially it looks like a red, but after charging for some time it turns into green? No, it doesn't work that way, right? Okay, a resistance bands, those bands are fixed in color because it depends on the material that you put inside the resistor, the shape or the size of the resistor. Those things affect the resistance. If you're not doing anything inside the resistor, you're not able to change the resistance. Therefore, from here you can know that this R here, similar like the capacitance, it should be a constant value. R here should be a constant value. Okay, so if R here is a constant value, but we know that the VR is decreasing, but R is constant, that means the only term that can be reducing here or decreasing here should be the current. So current here should be decreasing. Okay, let me, for consistency sakes, also label this as constant first. Okay, so from this simple discussion here, we are able to come to the conclusion that the charge should be increasing, the VC should be increasing, the current should be decreasing, and the voltage across the resistor should be decreasing. So these are the 4 important points that you should know based on this simple discussion over here. So right now I'm going to progress and look at this chart over here, a simple diagram over here, which show how it goes from uncharged to become fully charged. Okay. So initially you have an uncharged capacitor. So an uncharged capacitor, if you look inside it, it should be neutral for both plates. So something like this. Okay, so both plates should be neutral, so it should be balanced by the same amount of negative charge. Okay, so if you look at this situation over here, you know the amount of charge stored here is positive 0. There's no charge being stored at all. The amount of charge being stored here is negative 0. Okay, still haven't started charging yet, and therefore the potential difference across the two plates right now, this is VC, right, will be equals to 0 at this moment. Then therefore you can know that also Q is equals to 0 at this moment. Okay, but we know that this is Vs. Vs is a constant value. We are not going to change it. So later we'll be studying Vr, and we'll be studying the current passing through everything here, which is called I. Okay, current is in opposite direction. Sorry. Oops. Okay, so before that, when it's uncharged, we're going to close the switch in order to start the process of charging, right? Okay, so maybe there's a switch somewhere, and now we close the switch so that the process of charging starts. So the process of the process of charging starts. We are going to set that time as time is equals to 0. Oops. Okay, so time is equal to 0 at this moment. So if you wish to investigate again the same equation, Vs is equals to Vr plus Vc. If we open it up, this would be Vs, this would be IR, this would be Q over C, right? Okay, so what's happening at time is equal to 0 is Vs is still Vs, that's nothing has changed. But we know that at this moment, the current should be, the charge stored, there's still no charge stored at all, right? So the charge stored over here should be equals to 0. Okay, the capacitance is still the same capacitance, so it's unaffected. And because this charge stored is equals to 0, that means by this whole Vc over here will be equals to 0. Okay, so we can therefore come to a conclusion and say that this Vc at this moment is minimum. So minimum means by it's equals to 0. Okay, and at the same time, we know that Vs over here is a constant value. So if it's a constant value, but one term on the right hand side is equals to 0, we know the Vr over here will immediately just be equals to Vs, right? So we can come to a conclusion, Vr at this moment is at its maximum. Okay, because later when Vc increases, Vr will have to decrease, right? So now if Vc is at its minimum, Vr will be at its maximum. So what is maximum over here? Vr will just be equals to Vs at this moment. Okay, Vr is just equals to Vs at this moment. Is it clear enough? Maybe I write it again. Just write equals to Vs. Okay, so if we know this value here, it's maximum, that means IR over here, we know that R is constant, right? R is not changing. So that means by what is maximum? The current will have to be maximum. So the current have to be maximum. R is not changing, but our I is maximum. Okay, so R is still the same R. Okay, so what we can say from here is that our current is maximum. But our charge is minimum, which is equals to 0, uncharged. Okay, this is what happens initially when we start charging. But right now, if we let the process of charging happens, it will slowly progress until the point where it will be fully charged, right? Okay, so you might be wondering how long does it take to be fully charged? The amount of time it takes to fully charge is actually forever. Okay, a capacitor technically or theoretically cannot be fully charged. You take forever for it to be fully charged. Okay, but later on when later on we'll come back to this idea, why does it take forever to be fully charged? Okay, but for now let's just take it as it takes forever to be fully charged. Okay, but the focus is the process over here. During the charging process, from our discussion earlier, we really know that the Q will increase. At the same time, your VC will increase. On the other hand, your current will decrease and your VR will decrease as well. Okay, so by the end of the process, when we become fully charged, then I assume fully charged is something like this. Okay. Okay, so right now up there will be a fully charged positive Q. And then down there, let's just call it Q naught. Q naught means fully charged, right? Okay. Down here there will be negative Q naught. Okay. Please do not confuse this with the with dielectric, without dielectric kind of knot. In this case, the knot just means it reached its maximum already. Okay, it doesn't carry the meaning similar like section 1. Section 1, the meaning of it is like, oh, if knot is without dielectric, without knot is dielectric, but this is a different thing. Okay, you don't use it's the same symbol but it carry different meaning in different situation. In this case, in the charging situation, it means it reached its maximum already. Okay, so right now we can say that the charge stored across them will be the maximum already. So Q at this point has achieved its maximum, that is Q naught. Okay, if you look at the potential difference over here, the potential difference across the capacitor, because it's V is equal to Q over C, right? If your Q reaches maximum, your VC should also reach its maximum. So VC maximum is called V naught C lah. Peak. Okay, V naught C. Okay, this is still the same old VS, nothing has changed. But the voltage across the resistance later we know will drop lah. Okay, will drop until maybe 0. Okay, so the current over here will also decrease as well based on what we have discussed just now. Okay, so this is current. Okay, so this is at time is equals to infinity. So time is equals to infinity. It's still the same relationship that holds. Okay, the same conservation of energy still holds over here. So the first sentence still hold. The second sentence here still hold. Resistance, their voltage is of course based on Ohm's law. Okay, let me space it out a little. Still based on Ohm's law, nothing has changed. For the capacitance, it's still based on the ratio of Q over V is C. So that's it. Yeah, so from there we can come to the conclusion Vs remains the same, but right now our charge has reached its maximum, right? So because charge has reached its maximum, I'm going to use the symbol Q naught right now. Okay, the capacitance still remain the same, so don't worry about it. Okay, the resistance is also the same resistance. We say that the color bands won't change, right? But right now the current has already dropped to 0. Okay, again, why is it? Let's go through the sequence of understanding once again. First of all, you have a maximum charge. Okay, your maximum charge causes your VC over here to reach its maximum. So when it's maximum, it's equals to Vs. Okay, so if my voltage across the capacitor is at its maximum, which is equals to the voltage of power supply, that means by my voltage across the resistor will have to drop to 0 lah. This has to be 0, only Vs is equals to Vc, right? So you know that my voltage across the resistor has already gone to the minimum. So as minimum over here, it's equals to 0. Okay, so how does it goes to 0? Again, this is constant. Okay, let me just keep things consistent by labeling everything. Okay, so how do you get a minimum 0 VR? Your R is constant, you cannot change it, so you can only change the current. You have to change it to become 0 so that the VR will be equals to 0. So right now you have minimum current. Okay, so this happens at time is equals to infinity. Okay, so here there are 4 quantities that we have studied in great details. Okay, ignoring the voltage across the power supply, we have studied 4 quantities in greater detail, which is the charge stored. Against time, it will be increasing. The voltage across the capacitor, it should be also increasing with time. Then you have the volt current, okay, current, ampere, so it's volt, okay, against time. And this one you have your VR, which is volt against time. So there are 4 things that you have studied against time. You know that the charge should be increasing during the charging process. Let me just label it for our own reference. The voltage across capacitor should be increasing, the current should be decreasing, the voltage across resistor should be decreasing. Okay, so what kind of shape does it trace during the charging process? Means that as charging goes on, how does it increase? Does it increase linearly? Does it increase exponentially? Or does it increase this way? To understand what kind of shape will it trace, right, I will need to bring up an animation that I've made in order to understand the situation. So, okay, so let me switch over to an animation that I've made. Oh, where is it? Here. No, this one, not this one. This one. Okay. Okay, so right now we are going to study a charging process, but right now this is in animation form. The purpose of me showing this animation is to convince you that why it follows a certain shape. Okay, this one can be understood by just following the idea over here. Okay, so this is a charging process. Again, you have the same capacitor, resistor, and the power supply. The power supply here functions to pump charges from the negative terminal plate to the positive terminal plate, right? So what happened is this battery over here provide a certain force. Okay, what kind of force is it? Okay, if you're thinking this is maybe related to electromotive force in chapter 3, definitely no. Okay, electromotive force is not the force in the first place. It's just a bad naming. Okay, so don't worry about electromotive force. This is not related to that. This is just standard. You have high potential, you have low potential, you have chemical energy, bring it from low potential to high potential, that kind of force. Okay, don't worry too much about what kind of force is it. Just know that the battery supplies chemical energy to pump the charges from low potential up to high potential. This is a difficult process. That's why you need an external force to make it happen, to go from low to high. The external help is the battery. So the battery is providing that external force to push it from low potential to high potential. Okay, so because of this force, you're pumping positive charges from this lower plate to this upper plate over here. So there's a loss of positive charge in the lower plate, whereas there's a gain in positive charge in the upper plate. And you can see here I've created another arrow, but this arrow is in the opposite direction to the force by battery on charge. Okay, this one is supplied by the battery. The battery has chemical energy, is going to push charges in this direction. In this case, this is clockwise. Okay, but you can see that because there's an accumulation of positive charges over here, positive, they are supposed to repel, right? So if you add more positive charges into it, they will become positive. This plate will become positive. So the positive will try to repel other positive charges. So that's why we start to have a repulsion force over here. The positive will want to push the other positive away from the plate. So they want to push it out from the plate. So there's a bit of repulsion over here. Okay, so the number of positive charges increases on the upper plate and the number of positive charges decreases in the negative plate over here. So there's an accumulation of charge, positive Q and negative Q over here. So that's why we are going to say that the amount of charge stored in the capacitor increases. Okay, how do you relate to the voltage? You know that the accumulation of positive Q and negative Q, based on chapter 1, we will create a uniform electric field in between the two plates, right? So the uniform electric field here can be expressed in terms of this equation, where you take the potential difference, V high minus V low, or divide by the distance between the two plates, which is D. Okay, so you also know that C is equal to Q over V. This is just a definition of capacitance. So you know that the increase of E the presence of this E due to the accumulation of charge, the increase of E will cause an increase in the potential difference. And why there is there an increase in E? Well, the increase of Q here causes the existence of this electric field. Okay, so Q increase, C remain constant, is still the same capacitance. Our capacitance never changed. So if our Q increase, the V will increase. Okay, so there's two ways to explain it. First is the electric field gets stronger, so the potential difference across the plate also becomes larger. The second way is to explain using the definition of capacitance, where if you have accumulation of charge, the potential difference across your capacitor will also increase as well, where the C goes constant. Okay, so these two here prove to you that if Q increase, V will increase along the way. Okay, so continuing on our journey, what we want to study right now is if we let this charging process continue to go, now there's even more positive charges on the upper plate, there's even less positive charges in the lower plate. So we now see that it actually increases slower. If you refer to before this, I already pump up 3 charges over this. But as time goes by, you can see that I only pump 2 charges through right now. Less than what happened just now. Just now it was 3, right now it's 2. Why is the number of positive charges increasing slower in the upper plate? Why is the number of positive charges decreases slower at the negative plate right now? The reason is because, okay, here there's a charge store, but it's increasing slower. It's because of this repulsion over here. Right now there's a repulsion over here. It's as if it's not so easy anymore for the battery to pump charges to the upper plate. There's some repulsion here. There's some resistance. We don't want any more positive charge to come in. Please, we don't want more. We are really hating each other right now. We want to push each other out already. Please don't send in more positive charges. But this battery continues to send. But it's now facing some resistance. That's why the battery can only send less right now. Okay, due to this repulsion, it can only send less right now. So the Q will continue to increase, but right now it's not increasing that fast anymore. So you should expect a decrease in the gradient. Just now it increased very fast, now it increased slower. So based on the same idea, the increase of the uniform electric field will also increase the potential difference as well. Just like what we discussed earlier. Okay, so if you think about it, just now initially there's 3 charges flowing up to the upper plate, but now there's only 2. So you can see that the charges that is flowing in this circuit over here, if you're able to apply a microscope to look inside, not microscope actually, if you're able to zoom in and look inside, you see that initially there's more charges flowing, but right now there's less charges flowing. We know that current here is just a flow of charge. So initially there's a lot of flow of charge, but now there's less flow of charge. You should expect that the current to drop. Okay, so this process here, there's even more accumulation of positive charge. Therefore, the repulsion will get even stronger. There's an even stronger resistance right now. So if you continue on the same idea right now, there will be even less charges that can manage to get through to the upper plate. Even less right now because the resistance just get larger and larger to the point it's very, very difficult to put in another charge. So at that point, you should expect that the charge increase to be even slower, increases even slower, decreases even slower. That's why it will slowly approach a plateau. Okay, the voltage also the same. They become greater, the uniform electric field, therefore the voltage also increase. But you can see just now it's 3 charges, now it's 2 charges, then now it's 1 charges, so it further decrease. Okay, so from here you can slowly trace out the shape of the graph already. This one will be increasing to approach a plateau. The voltage will also increase to approach a plateau, whereas the I will decrease till near 0. So at certain point, which is at infinity, time is equal to infinity. At that moment, what happened is the repulsion is so strong that the battery cannot push anything in already. The force exerted by the battery is balanced by the force that is caused by the repulsion of the positive charges. Here is trying to push with 5 Newton. Here is also trying to push away with 5 Newton. So the force become balanced already. No charges can enter anymore. So this happens at time is equals to infinity. But because time is equals to infinity is happening at somewhere very, 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 very long time later, it cannot really fit in the graph. That's why we say we approach the maximum charge as an asymptote. You never really touch it, because if you want to touch it, you need to touch at time is equals to infinity. But that is just not in the graph. That's why we approach till not we approach V0 but never really touch it. I0 also the same, we are going to approach 0, okay, but at some point in the future there will still be another charge moving into the positive plate, and at some point even longer there will be another one drop of charge going into the upper plate as well, but that is going to take an infinitely long time, so therefore it never really reaches 0. The current will still flow, but it will flow very slowly, that it never really stop flowing until when it's full. It's supposed to be the end of time already. Okay, time is equals to infinity. That's why this is the kind of shape that you are supposed to trace for the Q, for the V, and the current. Okay, so this is when they are equal to each other, then the flow will not continue, it will stop flowing, no longer increase, no longer decrease. So it has already reached its maximum. This is what happens at infinity. It reaches maximum already. The last charge has already moved in, can no longer push in any other charge anymore. Okay, then of course you can see that the uniform electric field has achieved its maximum. That's why the potential difference across the plate has already achieved its maximum. Again, this is happening at infinity, so it does not exist on this graph. Okay, it's somewhere very far away, long time later. Okay, so the current also approaches 0. So this is the graph that we are supposed to get for QVC. This is voltage across the capacitor, and I. Okay, later we'll go on to discharge, but for now, we already understand the idea of how the graph should looks like. So let's fill in the graph right now. Oops, okay, this graph over here. Okay, so the graph should look something like this. Okay, there will be a maximum amount of charge stored, which is Q0. There will be a maximum amount of voltage over here, which is called V0C. Okay, so these two, they approach this Q0. This one, they approach this V0C. Whereas for current, just now you already see that current will drop from its maximum, approach 0. So from maximum approach 0. So we know that VR also follow the same trend as current based on Ohm's law. So it will also drop to near 0. Okay, so knowing this, right, we actually can attach equation to it. This is an exponentially increase or decrease kind of equation, increase kind of relationship. So there's an equation for it. So for this one, it will be Q is equals to Q0 1 minus E negative T over tau. Okay, tau is a new thing which I will explain later. VC will be equals to V0C 1 minus E negative T over tau. Okay, whereas this up here, these two are for increasing, right? This is for increasing. For decreasing, of course, the equation will be different. The equation here will miss out a 1 minus. Okay, so right now the equation will be I is equals to I0 E negative T over tau. Okay, whereas this one is VR is equals to V0R E to the negative T over tau. Okay, if you ask me where does all this equation come from, it comes from experiment. You know that the graph change like this. So this is an exponential kind of graph. So you know the exponent, the standard form looks like this. So you just need to put in the maximum current over here, the maximum voltage over here, the maximum voltage over here, the maximum charge over here. Then you can see it's just a standard exponent, a negative exponent. So there's a 1 over tau over here, which I'm going to explain later. But this is the equation that you can have. Okay, you can derive it, but the idea just comes from, it's a first order differential equation. It's mathematics stuff. You can look up first order differential equation. I think in maths you learn about it, but that's how it should look like. Okay, so now let's go on to the last thing which I want to explain today, which is this tau over here. What is this tau over here? Let's try to understand it. Tau, the name tau here is actually called time constant. So time constant has a symbol of tau. Okay, this is a Greek letter tau, and because it's time, right, the unit is just second. Okay, so right now I'm going to write down the definition of a time constant, but we actually need to really understand what's the meaning of it. So let me just write it down first before I explain. It's the time taken for something to something to something of its maximum value. Okay, so we want to understand what happened when the time of charging has already reached a certain value, which is tau. When we charge by an amount of time, which is tau, what happened to the charge stop? What happened to the voltage? What happens to the current? What happens to the voltage? Okay, to do that, let's probably flip to a page over here and try to understand it. Okay, we have two versions of equation. One is the increasing equation, which is let's say Q is equals to Q naught 1 minus T over tau. Okay, then we have a decreasing version of the equation, which is I is equals to I naught E negative T over tau. So let's investigate what happens at time is equals to tau. When time is equal to tau, what happened? Because we know that tau is the time taken for something to happen. So let's see what happened at time is equal to tau. At time is equal to tau, you can say Q is equal to Q naught 1 minus e to the negative tau over tau. You can say you can sub in time to become tau. So tau over tau is just 1. So if you put it inside here, you get this value over here. Okay, this value over here, if you put it into a calculator, it's 0.63 something something something. Okay, so this is actually just means by 63%, 63 point something something percent of Q naught. Okay, so you can see that at time is equals to tau, your charge has already charged up to 63% of the maximum value. Okay, how about if you use the decreasing equation? You sub in the time is equals to tau. Time is equals to tau. What happens is it becomes tau over tau. So this time the equation is slightly different. It's not 1 minus e to the power of negative 1. It's just e to the power of negative 1. E to the power of negative 1, if you put it into your calculator, it's about 0.37 something. So this is 0.37 of I naught. So what does this tell you? This is about 37% of I naught. Okay, so that means you drop to about 37% of I naught at this particular time. Okay, so looking at these two working, we can say that when we charge until a level which is called tau, let's say this is the time which is tau. If you go check what is the charge stored at that moment, you find that the charge stored at that moment has already reached 63% of the maximum. So it's 0.63 of Q naught. Okay, the same timing over here, okay, the same timing over here, tau, will, if you check the voltage of across the capacitor, you also see that the voltage across the capacitor is also 0.63 of V naught C. Okay, continuing on that, the same time over here, tau, if you go check the current, you see the current has already fallen to about 0.37 of the maximum current initial. Then if you look at the tau, the time over here, the same amount of time, you see that the voltage across the resistor has also dropped to 0.37 of V naught R. Okay, so it's just a time that we usually reference. Okay, it's a reference time to let us know how much time it takes to charge until a certain level, how much time does it take to fall to a certain level. Okay, so if I tell you today I have two charging circuit, one charging circuit is 100 second tau, one charging circuit is 200 second tau. That means the first circuit takes 100 seconds to reach 63% of maximum charge, whereas the second circuit takes 200 seconds to reach the maximum amount of charge, to reach 63% of the maximum charge. So that means what? The second circuit charge actually takes a longer time. It charges using a longer time, whereas the first circuit you only take 100 seconds to reach the 63% charge. It takes shorter time. Okay, it's somehow like all those kind of smartphone nowadays. Don't they usually tell you that it 10 minutes to 60% charge or 5 minutes to 37% charge? It's some kind of this kind of value. It tells you how fast does it charge. If the time constant is a very short, it's a very small value, that means it can charge very fast. If a time constant is a very big value, that means it takes a very long time to reach that certain amount of charge. Okay, so in this case, we already set the benchmark is 63%. If it's going up, if it's going down, it's 37%. Okay, so for this graph over here, we can definitely see that we have Q, which is increasing, and we have VC, which is increasing. Okay, so we can say it's the time taken for Q and VC to increase, right? But increase until what stage? Okay, we already said that this is until 63% of its maximum value. Okay, on the other hand, if you're focusing on the current, or if you're focusing on the voltage across the resistor, then this time it's not increasing, this time it's decreasing. Okay, but this time it decreased until what level? This time is 37%. Okay, hope student can still remember that 63 come from this value, 1 minus e to the power negative 1. Then whereas 37 here come from e to the power negative 1. Okay, so this time constant here sort of signify how fast or how slow a circuit charges the capacitor. Okay, so it's a good reference for us to know whether the capacitance suits our purpose or not. Okay, let's say in electronic circuit, you want it to charge very fast, you find a time constant very small kind of circuit. If this situation here requires a capacitor to charge very slow, you find a charging circuit with a big tau, so it's some kind of a reference value. Okay, so I think I have covered what I want to cover for now. So the idea is we talk about charging circuit, we learn about which kind of value increase or decrease during the charging process. Then we learn that it never really charge until full, it takes an infinite time to charge until full. And you know that if you look at this value tau over here, it will be equivalent to how many percent, which is that very specific percent, 63 for increasing, decreasing 37. Okay, oh, another important thing, this tau over here actually, this is actually extremely important. Tau over here can actually be determined very easily without doing the experiment. If you happen to know the resistance and you happen to know the capacitance, this tau over here can actually just be determined using RC. Means that if you know the resistance over here, and if you know the capacitance over here, if you know the R and if you know the C, what you need to do to find the value tau here is just to take the R multiplied by the C. If you take R multiplied by C, you get this tau, and this tau, if you check at this particular moment tau which you calculate using RC, you see that at that particular moment, the charge has already reached 63% and the current has already dropped to 37%. It's quite a magical thing. Just by taking these two simple values and you multiply it, you get this tau over here, which will indicate how fast it charges. Okay, of course there's a lot of inner working behind it, but that's not what we want to cover in this particular video. Okay, so for now, I hope you are clear with charging circuit. Then in the next video, we are going to move on to discharging circuit.